Hope you're doing fine today. Because today we're going to meet the social side of our software architecture. And the reason I want to give this talk is because I have noticed that we as an industry, we tend to talk a lot about the importance of teamwork, the power of team autonomy. But at the same time, I have seen that it's notoriously hard to get those things right. And when we fail, we tend to fail miserably. So in this session, I would like to approach software development from a different side, from the people side, through the side of social psychology. And you might ask yourself, why do I feel qualified to talk about this? And it's a very valid question, because you're going to spend 45 minutes with me now, right? So let me share a little bit about my background. I started as a software developer back in 1997. I'm an electrical engineer to start with. And after the first 10 years in the industry, I started to notice a pattern. I noticed that every single large-scale project that I saw failed, and it tended to fail brutally. And the way those projects failed was that they were often over budget, they delivered much less features than promised, and quite often they delivered with a number of known defects. So I started to think, why is it so hard to write good code? And I kind of realized that I won't find the answer to that question within the tech industry. So I decided to do something different. I decided to start to study psychology. And it turns out that psychology is really fun, so I ended up spending 6 years at the university. And what I try to do these days is to take my psychological perspective and put it on top of my technical background. And I've written 2 books about that, Your Code is a Crime Scene, and the new one, Software Design X-Rays. Now, when I tell people that story, the single most common question I get is, but yeah, what did you find out? Why is it so hard to write good code? And I find that a truly fascinating question. It's a good question, but it's also the wrong question. Because I have to tell you, the more I learned about psychology, the more surprised I got that we're capable of writing any code at all. It just shouldn't be possible, right? The human brain is way too limited. Software should be too hard for us. And yet, we do it every single day. And sometimes our code even works. So, the reason we managed to pull that off is because the human brain has come up with a bunch of strategies, a bunch of workarounds and shortcuts that we can use to cram all that complexity of software into our head and reason about it. Now, what I found so fascinating is that the brain's tendency to look for workarounds and shortcuts, it might serve us pretty well in simplifying something very, very complex. But it can also serve us less well in a social setting. And the result in that case is what we refer to as social biases. Now, social biases, I'm going to mention some of them today. They are there for a reason. And the reason they are there is because they do help to simplify complex decision-making in complex situations. However, the end result might not always be the best. Because social situations, like software development, is a very complex process. And I would like to explain why it's so complicated by taking you through a controversy. Now, when I started to study a field called personality psychology, I learned about this controversy. Because it turns out in psychology, one of the best measures that we have is something called the Big Five. Has anyone heard about the Big Five before? 2 persons, great. So the Big Five is a very stable and reproducible measure. And it's something you use to assess a personality. So the basic idea is that you have 5 different broad categories. Things like, how open are you to new experiences? Your points on the extroverted, introverted scale. Neuroticism, things like that. And each one of your personalities is a complex combination of your scores on these 5 different dimensions. Now the question is, let's say that I know your personality score for each one of you. Given that knowledge, can I predict how you will act in a specific situation? One group of psychologists that started out with Big Five, they said that, Yeah, of course, that's what a personality is, right? But then there was another group of people who meant that, no, you cannot use a personality score for that. The situation is what matters. And when I started to learn about that, I immediately thought, hey, I've seen this before. This is static versus dynamic typing. This is Emacs versus Vim, right? So it's almost like this tendency towards strong opinions and controversies is a human thing. Who knew? It's truly fascinating. And like most strong controversies, the truth turned out to be somewhere in the middle. And I would like to read a quote from you from a psychologist called Michel. And Michel cites his research where he claims that 91% of the differences in people's behavior, how we act in different situations, cannot be accounted for by personality tests. So indeed, it turns out that social factors in the situation, have a stronger weight. But the personality is still important, because our personality kind of predisposes us to act in a specific way. Now, the reason I tell you this is because I like to view software systems in the same way. I like to view software systems as having both a personality and situational factors acting upon them. The personality to me, that's the code, that's the architecture. And just like people personality, a system's personality predisposes what we can do with the system. Some features are going to be easy to implement, others are going to be really, really hard. But no matter how good we are at the personality side here, no matter what our system score is on this fictional Big Five for software systems, what really matters is the situation. That's the strongest forces. And the situations are things like your culture, your organizations, your collaboration. And I will claim that those factors outweigh any technical aspects. I mean, no matter how miserable our code is, if we get the organizational side of it right, we might succeed. It might be more expensive, but we will succeed. And if we get the organizational side wrong, no matter how clean our code or our architecture is, we're going to fail. And we're going to fail brutally. And I would like to share a story with you to try to highlight that. I would like to tell you how you can make perfectly readable code unreadable. That's useful knowledge, isn't it? Right? Please try this out on Monday. Let me tell you. So this is one of my war stories from my previous life. I used to be a software consultant. And what happened here was that it's actually a pretty fascinating starting point. It was a company that were in a very good position. They were going to do a new version of an existing product. And they were in a good situation because they had historical data that showed them that using our 5 in-house developers, we can do this in 1 year. I know what you think. A software project that's predictable. Crazy. And of course, pretty soon someone from the marketing department came down and said, 1 year, that's not good enough. We need it in 3 months because we have this really important trade show. So let's optimize for that. And what they did was basically, how do you take something that you know is going to take 1 year and then you compress it down to just 3 months? What would you do? Yeah. We cannot be rational here. We need to think like managers, right? So after all, it's simple math, right? You just throw 4 times as many developers on it. And they did. Now, I wasn't part of the project initially. I came in later for, how should I put it, for the post-mortem. And my task was to kind of see if I can help out and bring it back on track. And one of the things I did was that I talked to all the stakeholders on the project. I talked to the developers, the testers, the managers, everyone. And all of them told me exactly the same things. Everyone complained that they had a lot of quality issues, a lot of defects. And this is not particularly surprising given what we actually know about the correlation between the number of developers touching a piece of code and the number of quality issues. But what really surprised me was that everyone claimed that the code is so hard to understand. And the reason this surprised me was because prior to those interviews, I had been reviewing a lot of that source code. And it's not like it was a work of art, but it was by no stretch of the imagination hard to understand. It was perfectly readable code. It was simply good enough. So this kind of surprised me at first. Why is that code so hard to understand? Why do I have that perception? But then it occurred to me, the reason that code was perceived as unreadable was due to this. When we reason about source code, we never have a perfect copy in our head. What we have is a mental model that might be imperfect. And what happens if you overstaff a project is that even if you write a piece of code yourself today, 5 days later, it's going to look completely different because 7 other developers have touched it in the meantime. And that makes it impossible to maintain a stable mental model. And that's also one of the reasons why they had so many defects, because suddenly you find yourself changing something based on outdated knowledge. Now, given what I just told you, how many of you think that this project finished in 3 months? Not really optimistic here, are you? Okay, but 1 year, that was the original data, right? And now there were 4 times as many people, so of course they could complete it in 1 year, right? Great, that's the spirit. But it's unfortunately not correct. It took them 2 years. And the only reason they managed to deliver was because, first of all, they had to cut the scope, and they had to deliver with a number of known defects. Now, think about that for a moment. They actually got less out of the project than what they expected in twice the time, using 4 times the cost. Does that sound like a good trade-off to you? I don't know, I've never been good at economics. But I do recognize that story, and I do think it shouldn't come as a surprise to anyone who has read The Mythical Man-Month. So The Mythical Man-Month, it's one of my all-time favorite technical books. I think it's absolutely brilliant, and it's still, large portions of it are still very relevant to this day. Now, The Mythical Man-Month got famous for what we now refer to as Brooks' Law. And Brooks' Law claims that adding manpower to a late software project makes it even later. And Brooks even has a formula for why this happens. This is what it looks like if we plot it. So what we have on the y-axis is the number of months until completion. And on the x-axis, we have the number of people that work on a project. And as you see here, to a certain degree, we can add more people and we can get a quicker completion date. But at some point, the more people we add to that project, the further into the future the completion dates. And the reason for that is because the number of hours that we have available increase linearly with the number of people we add, right? Typically 40 hours a week for each individual. However, the coordination costs, the communication paths, increase at a much, much more rapid rate. And at some point, the increased cost in coordination is going to consume all those extra available hours and then some. So we actually get negative productivity with additional people. But I do think that the effects we see, and this is something I've seen in so many software projects, and we might not even be aware that we are falling into this trap. And I do think that the costs associated with this are more than just coordination and communication. I also think that we have motivational factors. One such factor is something called social loafing. Has anyone heard about social loafing before? No? Good, I got something new for you. Cool. So social loafing is a type of motivation loss, and it occurs when we feel that the success of our team depends little on our own efforts. So what we do in that situation is that we pretend to do our part of the work, but in reality, we just try to look busy and hope that everyone else will keep up the good effort. And it sounds horrible, but it's a very, very human thing. And the reason we do that is because if the goals of a particular project aren't clearly communicated, or if we enforce arbitrary deadlines, people lose motivation in a task. And it also becomes so much harder in a larger project to see how my individual contributions can make a difference. So I think that's another reason for trying to keep teams really small, and we'll get to that soon. Now, I said that I've seen this happen so many times, and I still see it to this day. The Mythical Man-Month was published in 1975. So why do we keep repeating the same mistakes over and over again? I do think I have an idea, and I would like to test it on you. So please, have a look at the following piece of code. Who can tell me if this piece of code was written by a single developer in 1 hour, or if it's a constant coordination bottleneck between 5 different feature teams? Now, of course, you cannot tell. It's impossible. We just don't know. And this is what I would like to refer to as the great tragedy of software design, that the organization that builds the system is invisible in the code itself. And as a consequence of this tragedy, what we tend to do on software projects is that we tend to throw technical solutions at people problems, at organizational problems. And we start to treat symptoms instead of the real issues. Does anyone recognize something on that list? I would claim that none of those is really a technical problem. But since we cannot see the organization, it's simply not available in our code, we tend to downplay its importance. So, how can we improve the situation? Well, the first thing I try to do is to bring visibility to how it actually looks today. And I use a technique I call fractal figures. So let me walk you through this, and then we're going to see some examples. So what you see here is that I typically take each module, each subsystem, each service, each file, and I visualize them as a box. And each team gets assigned a specific color. And the amount of code each team has contributed to that particular module is reflected by the area of their box. So here we see that Team 1 has written the majority of a piece of code, and Team 2 is the second largest contributor. And so what I do next is that I try to normalize this so that we can do some calculations on it. And I'm using a formula from a paper I'm referencing down here. And I'm not going to walk you through the math. I post my slides on Twitter afterwards in case you want to look at them. All you need to know is that what this formula does is basically it takes a fractal figure like that and normalizes it to the range 0 to 1. So if we have a module that's written by a single team, then it's 0. And the more fragmented our development efforts, the higher the potential coordination needs and team coupling, the closer to 1 we get. That's all you need to know. Are we good? I didn't mean to do that math thing to you now in the morning. Now, the only thing we need, now that we know how we can find team coupling and coordination needs, we only need to get some data. And it turns out we all already have all the data we need. And those of you who might have read one of my books, you know that I'm a big fan of version control data. And the reason I'm a fan of version control is that I find it so fascinating that historically we have used version control more or less as an overly complicated backup system and occasionally as a collaboration tool. But in doing so, we have built up this wonderful data source that can give us insights into the social side of our code, because our version control system knows exactly which developer that wrote which piece of code and when they did it. And that's something we can aggregate into teams. The main drawback I find with version control data is that it's very file-centric. And when we reason about architecture, we are more interested in higher-level building blocks. So what I tend to do is I tend to group the file structure to different logical components. I simply aggregate all the contributions to a bunch of files or a bunch of folders, and that's the level I do the calculations on. Okay? With that covered, we have everything we need to uncover some social ways to fail with software architecture. And I would like to walk you through a number of architectural patterns and investigate the social forces that act upon them. And I want to start with this one, a classic. Who recognizes this pattern? Yeah, that's all of you. Great. This is model view controller, right? It's very common. Now, I analyze code as part of my living. And when I go to different organizations, I always start by asking them, what kind of architectural patterns do you use? And 9 times out of 10, they say, we have a model view controller. But then you look at the code, and this is never, ever what it looks like. And the reason for that is because we know we need to have some services layer, right? Where you can stuff some business logic. We also know we need to have a repository layer. And the reason we need a repository layer, I have to admit, is still somewhat unclear to me. But I've been thinking about it a lot, and I haven't really come up with a good reason, so I'm just going to call it a best practice, so I don't have to motivate it. Now, of course, that's not enough. We also know that we need a data abstraction layer. And the reason we need a data abstraction layer is because otherwise we couldn't get to exercise all our mock frameworks, right? So this is clearly important. And of course, it's very good to introduce some view models, because if a level of indirection is good, 2 levels of indirection has to be better, and so on. So it's not uncommon to see layered architectures with 10, 11 different layers. Does this look familiar? Some of you nod. Now, the fascinating thing here is, what happens when we need to add something to that layer stack? Let's say we want to add a checkbox in the user interface. What do we have to modify? Everything, right? I actually have pretty good data that I've collected over the years, where I can show that somewhere between 30 to 70% of all commits you do in a layered stack like that is going to ripple through the entire architecture. And that lower number is for systems that are in something called like a stable maintenance phase, where most of the things you do are bug fixes. And bug fixes do tend to be more local. The higher number is for systems under active development. So I don't know about you. I told you that I'm not good at economics, but this looks pretty expensive to me. So why are we doing this? The main motivation that I always hear for layers is that we want a separation of concerns. Has anyone heard that? Do we have a separation of concerns? Yes, we do. But what kind of separations? It's a technical separation. Each one of those is a technical building block. And this is in conflict with the work we do every single day, which tends to be use case-centric, feature-oriented, and end-user-oriented. Right? So we have a conflict between the kind of work our architecture supports and the work we do on a daily basis. So what's the consequence of this? Yeah, first of all, I do think that the change patterns are expensive, because we have a lot of code here that doesn't really do anything. But it gets even worse when you put multiple teams on a layered architecture. So let's go back to our fractal figures and visualize it and see how it typically looks on a layered architecture. So what I've done here is that I'm visualizing each one of the layers as a circle. And by the way, those examples, they are based on real-world systems. I just made them anonymous in order to protect the game. But what you see here, each circle is a layer, and the color reflects its fractal value. So the more red, the closer to 1 we get, the more fragmented the development efforts, the higher the team count. And what we see here is basically that the whole architecture is a gigantic coordination bottleneck for different teams working on it. Why is that the case? Yeah, of course, we see services, administration views. Those are technical concerns. So again, if I want to add a feature, I have to let my team work on all over the place. So I do think that this data helps us answer one of the most common questions. And it's this question: should we use component or feature? We kind of tried both, and none of them seems to really work. So what tends to happen here is that many organizations, they might start out with component teams because it seems a natural way to organize. And what you quickly find in a layered architecture is that you get extremely long lead times, right? You get all those handovers, and you get a lot of focus on those APIs. So you decide that we need to shorten the lead times, and I've been to this Agile conference where I heard about feature teams, so let's do that instead. And pretty soon you find that your whole architecture is a gigantic coordination. So how can we resolve this? Well, I do think there is some wisdom in an old quote. I don't think we can fix what is fundamentally an architectural issue by purely organizational changes. Those two always need to go together. So to me, trying to have multiple teams on a layered architecture like that for a business application, I don't know, it's a little bit like, you try to play football with a cement lump. It's going to be a slow game. And it's not going to be quicker just because you switch to basketball. It's the raw material that has to change. And I do think that this effects that I've seen in virtually every layered architecture I have investigated is one of the reasons for the recent hype and popularity of microservices. So how many of you do microservice architecture? Wow, that's a majority. Interesting. So Let's look at some of the most common arguments for microservices. The single most important principle that I hear about is that we want to have loosely coupled systems. Because if we have loosely coupled system, we get a lot of good stuff. We can have highly autonomous teams, right? We can minimize the team coordination. And as a consequence of the loose coupling and team autonomy, we can scale and deploy our services independently. It's a wonderful word, isn't it? Now, I do have a lot of data on microservices as well. So I would like to show you the same team-level coordination view that I showed you for the layered monolith. So here's some data from a real-world microservice system. Do you see the difference to the layered monolith here? Neither do I. The labels are slightly different, but again, it looks like the whole system is a gigantic coordination bottleneck for all those different teams. And in this case, the organization had chosen to use features. Why does this happen? We wanted to have microservices, right? We wanted to have highly autonomous and independent teams. Well, for those of you who sit close up here, if you can read the name of those services, you see that they have names like translation server, access control server, diagnostics server. And to me, that sounds a lot like technical boundaries, right? Like technical building blocks. So again, it looks like if you want to implement a feature, it seems that, again, we have to modify multiple services together because the way our architecture is structured misaligns with the work of the team. So to sum up this first case study, we had everything tightly coupled because we need to modify all services if we want to add a new feature. As a consequence, we get very low team autonomy, and of course, we cannot deploy anything. So to me, this is a mix with the worst of two worlds. We have the inflexibility and costs of a layered monolith together with the excess complexity of building a distribution. So, of course, maybe this is due to a lack of modularity. Of course, we shouldn't build those relatively large distributed layer services. So maybe small and modular services will solve the problem. Well, I have some data on that as well. But before I show that to you, I want to take a minute and talk a little bit about accidental complexity. I want to point out, when I talk about accidental complexity, I've found that there are two different kinds of accidental complexity. The first one is when we have complex parts. So this is where you pick up that file and you find all those nested conditional statements that are really, really hard to understand. That's a complex part. But then we have the other side of complexity, and that's where each part is easy enough to understand in isolation, but where the emerging system behavior is anything but simple. And I do think that this second kind of complexity is something we will see a lot more of due to the popularity of microservices. So, with that covered, how can we detect that second kind of complexity, complex interdependencies? If we could that, we can use that to evaluate our microservice architecture. Well, the approach I use is something I call change coupling. So change coupling is very, very different from how you typically view coupling, because change coupling is invisible in the code itself. It's based on the process of working with it. So here's a brief summary. Let's say we have 3 different services. And the first time we add a new feature, we need to modify the subscription service and the sign-up service together. The next time, we modify something else. The third time we add a new feature, we're back to modifying the subscription service and the sign-up service together. So if this is a pattern that continues, then we know that there is a kind of relationship between the subscription service and the sign-up service because the teams are always changing them, referring the same issues or the same things, right? So they have to be logically connected. This is something that we can use to evaluate microservice dependencies. Here's an example. Have a look at the following visualization. This visualizes change coupling. And each one of those labels visualizes or represents a microservice, and the connections between them shows the significant change coupling. Now, what I've done here is that I've highlighted just one service and its dependencies. It's a service called estimated conversions. And when we change that one, we have a predictable change in 7 other services. Is that good? I don't know. I was never good at it. Now, what about the second case here? Just to show you that it wasn't a fluke. We have something called estimated profit. We change that one, and we have a predictable change in 5 other services. Wow, this looks expensive. But those expenses are nothing compared to what happens when you put multiple teams upon that architecture. Because this is what your coordination map is going to look like. Now, what you cannot see here is that the actual services, as represented by those circles, are much, much smaller than in my previous example. In the previous example, there were pretty gigantic services, 50,000 lines of code, stuff like that. Now they are much, much smaller. What we talk about here is maybe 500, 1,000, 2,000 lines of code. So pretty small modules, easy enough to understand in isolation. But look what happens. We have 5 free teams working in each one of those services. Why does this happen? Well, due to that excess change coupling, it's a clear indication that when you add a feature, you have to touch multiple services. So it's very likely that at any given time, you have multiple teams working on different features that need to coordinate their work via the code. And the main reason for that is, again, even if the services are more modular, we can maybe question the level of modularity by looking at the names here. We see that the services are called things like payment accepted, payment received. And to me, that sounds something like a state, but it might not be a good service boundary, right? So I will claim that what we have here is not so much services as distributed objects. And as a consequence, as we saw, we have a tightly coupled system, even though it's distributed. As a consequence, we get very low team autonomy, and again, we cannot deploy a single service in isolation. Now, at this point, some of you might be thinking that what I have showed you so far isn't really microservices, but more microservices, right? And you would be right. But that's not my point. My point is that microservices or software architecture in general is incredibly hard to do right. And when you design an architecture, you're also doing social design. And if we forget that, everything is lost. So, what can we do about this? I do think it all boils down to a single simple advice, that we need to align our architecture and organization. And this is, of course, something that is at the core of Conway's law. And I would like to look a little bit at how what we typically interpret as Conway's law impacts modularity. What I have found is that when we manage to align our architecture with the problem domain, not the solution domain with technical building blocks, with the problem domain, we tend to create natural team boundaries. Because that's typically the level we tend to parallelize our tasks. So I want to show you some examples on how we can do that. Can we do it with microservices? Can we align our microservices with the problem domain? Yes, of course, we can. It's definitely possible. I've seen some teams and organizations being very successful with it. But what I wanted to point out with my previous case studies is that microservices won't auto-magically resolve that, right? Microservices is no guarantee at all that we manage to create that alignment. In particular, microservices definitely won't cure our dependency blue. There's nothing inherent in microservices that guarantees loose coupling. The couplings are going to be there, they're just going to be implicit instead of explicit. So it's still up to us to manage that. What I've found as a common denominator between those organizations that are successful with microservices is that their services, they tend to be pretty small, they tend to be team-sized, and they are always partitioned by business capabilities, not data-centric. And what do I mean with a small team? Well, based on the research I read, small team is around 3 people. It's really, really small. Because beyond 3 people, we run into all those coordination issues and motivation bias. So as a rule of thumb, 3, maybe 4 people. So it's smaller than we would like to think. It's smaller than I would like it to be. But I do think the advantage is that with small teams, we do get rid of that coordination overhead, and in particular, we minimize the risk for motivation losses like social loafing, because it gets so much easier on a small team to see how my contributions really make a difference. Now, what can we do with our layers? What do we do instead of layers? Well, one pattern that I've been using a lot is something called package by component. That's a very good write-up by Simon Brown down here that I really recommend that you check out. And the idea with package by component is that instead of identifying those technical vertical building blocks, we identify whole slices that represent a particular business capability. So we structure our architecture according to the business capabilities. Now, this makes it easier to provide natural boundaries for the teams. But there's one common pitfall that I've seen with package by component. There's still one big potential coordination bottleneck. Can anyone guess what? Right? The database, the black hole of maintenance efforts in monoliths. Of course, we have to be really careful here. And what it basically comes down to, there's no quick fix for this. What basically comes down to is that we need to do a trade-off. We need to decide what's most important for us. And if things like loose coupling and highly autonomous teams are more important, which I tend to weight more favorably, then we need to trade off with the code quality here. What we basically need to do is that we might find that we need to duplicate some data. We might even find that some things that could be easily done in SQL, we need to rip it out and do it in application code instead. So it's going to be a trade-off, and it's going to be something we need to be aware of. But package by component do simplify the application code side of monolith. What I find particularly interesting with package by component is that it gives me a consistent macro architecture while letting me vary the technical details. So for example, this is something I use for the application I am working on right now, an application called CodeSyn. And what I do here is that we might find that some components could benefit from some additional structuring. So we might even do crazy things like layers, right, inside some components. Other components, they might implement a business capability that's so easy to implement that we might not even need a database. So we implement it in a single file. And this freedom to adopt the code to what the problem actually calls for is a big win, right? And it's a huge contrast to layered architectures, which basically says one size fits none, right? So here you can really adapt your code. And if you do this well, and you manage to identify those different components as business capabilities, you will create natural team boundaries. The teams might still have to coordinate in their APIs, but the whole implementation will be highly autonomous for each. Now, before I go to a last part in this presentation, I would like to share what kind of tools I use in case you want to try this on your own code base. So the first thing I like to point out is that I find it truly fascinating how far you can get with simple commands. So using just Git and the short log, you can basically get the coordination need per component, right? And I have a bunch of examples on this in my software design X-rays. When I start to work, but at some level, you do need some scripting on top of it to do more complicated, more complex. And when I started to work with this, maybe 10 years ago, there weren't any tools available that could do the kind of analysis I wanted to do. So I started to write my own, and I open sourced my initial experiments. It's a tool suite called CodeMath. It's available on my GitHub page. It's entirely free. So if you're interested in playing around with this, that might be a good starting point. What I work on these days is something called CodeSyn. So CodeSyn is the evolution of those ideas, and it automates all that stuff. And CodeSyn is available as a service as well that is entirely free for open source projects. So if you're interested in these kind of analysis, please have a look at CodeSyn and consider to support it. Now, with that covered, I feel that it's only fair that when I start to mention Conway's law, I also have to mention that it's on oversimplification. And the reason I say this is because if we take Conway's law to the extreme, we might run into other problems. And those problems are social. One specific example is something that social psychologists know as the fundamental attribution. So the fundamental attribution error is that when we attribute the same observable behavior to different factors, depending on if it concerns our group or the other group. More specifically, and quite problematically, we tend to overestimate personality factors when we explain the behaviors of others. So just to give you an example, let's say that your team breaks the nightly build. Yes, I know it's a highly hypothetical scenario, right? Play along, please. Now, when that happens, you know that you were under a lot of stress. You were really trying to meet this impossible deadline. You were doing your best, and the code that you, of course, didn't write yourself was a complete mess. And besides that, build pipeline has. So a lot of situational factors, right, that explains why you broke the build. Now, of course, when my team breaks the build, you know that that's because we are a bunch of lousy cowboy hackers, right? So again, it's a personality. So that's the fundamental attribution error at work. And as you know, I like to visualize things. So I try to see how can I come up with a visualization of the fundamental attribution error. And this is the best I could do. Now, what do we do about this? Well, it sounds like a contradiction, doesn't it? On one hand, I've been claiming that we want to minimize the coupling between different teams. We want to allow teams to work independently, but at the same time, we need to bring them close together to avoid stuff like the fundamental attribution error. Is that a contradiction? It's only a contradiction if we fail to distinguish between operational boundaries and knowledge boundaries. So what I mean with this, so the operational boundaries, those are the parts of the code where the team do most of their work. And I do think that those should be kept rather narrow, so that we have clear areas of responsibility. However, our knowledge boundaries, the parts of the code that we're familiar with, the people and the other teams that we know as individuals, those has to be much, much broader. And they typically have to include all systems that we somehow interface or relate to. So how can you make this happen? Well, the organizations I have seen that have been successful with this, they have used a number of patterns. The first is that they make it a habit to invite people from other teams to their code review or their design walkthrough. Not only might that give you an outsider perspective that you can actually learn from, it also helps you to get to learn people on the other team as individuals, which minimizes the risks for social biases. Another thing that I've seen works well is when you, as an organization, encourages people to rotate. I wouldn't enforce it, but if someone has the motivation to work on a different part, please let them do that. It's a good thing. The third thing I've seen that seems to work pretty well in large organizations to scale this is to adopt an open source inspired ownership model. So each team has a clear ownership of a particular component or particular subsystem. So they decide what goes into it. But anyone can submit a pull request. And what I like about this is that it can remove a bottleneck. So if my team is busy and the other team, we need a quick fix here, then I can do that fix myself. And since I'm used to take part of the code reviews and design walkthroughs, I have a fairly good idea of what I need to do. So I can just submit a pull request. And if I do it well enough, the team will accept it. So with that covered, I'd like to sum this up. What I wanted to communicate today is that an architecture never, ever exists in a technical vacuum. And as we have seen, the social side of our code will impact many important aspects like feature implementation efficiency, inter-team coordination, and lead times. And as I hope to show you today, I want to show you that you can actually measure and visualize the social side of code too. And it's an aspect of software development that should affect most of the high-level decisions. And if you want to dig deeper into this, I have my whole book about it. I blog about this regularly at ampere.com. And if you want to see some examples from well-known open source projects, I recommend that you go to Codes.io and Showcases, where I have a bunch of interactive analyses that you can explore and see if you find your favorite open source software. With that covered, I'm going to hang around for a couple of more hours at the conference. I'd be really happy to discuss this, so please just grab me if you want to talk about this. And for now, I just want to say thanks a lot for attending my session. Thanks a lot for listening to me, and may the code be with you. Thank you.